Alright, pointers in memory. We'll get through it together. Almost there. We learned like what pointers are, right? How to make them, what the types of things should be. It's always has to do with the type of what address you're holding. Like if you want to hold the address of it has to be an int star, right? So that's important. You can use the arrow operator. Fun stuff, a new way, like references, we're secretly using pointers. I actually have a question for us right at the start to see if we remember things. So you can discuss both, get into little groups and discuss both questions, but let me spell it out. So if I use a star in the type name of a variable, like I say int star p equals blah, 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 right? That's using a star in a type. What does that mean? Think about it. And then if I use a star somewhere other than a type, like, I don't know, star p equals star p plus 1, what does that mean? All right, so let's do, get both answers ready, but just enter your answer for the first one first. So if you use it in a type, what does it mean? And I'll stop attendance after we finish this question, so make sure to do that. All right, so think about it, discuss the answers to both of those questions, but just enter in the first one right now. Give you a couple minutes to discuss that. And also do attendance, because I'll stop that right after this if I remember. What are those names? What are those words? What are those? What are those not? Get both answers ready, but just do the first one. Another minute or so. I got 5 more seconds on my timer, and that's good timing because I think I hear the conversations dying down. Let's see what we're thinking. That's a beautiful graph. With a majority, we're thinking A. And yeah, in a type, that does mean pointer. So like P is a pointer to an int. You kind of read it backwards. Okay, so that is correct. A. And then let's do number 2 as well. Which one's that? So enter in your answer, please, for question 2. If I use it somewhere other than a type, like in an expression like this, it's used twice, right? What do we call it when we use it out there? I assume you're already ready, so I'll give you like 5 more seconds to enter it in. Stop this too now, right? Yeah. So I will end the question. Oh no. Well, this is why I asked. So star P, what it does is it follows a pointer to get to what it's pointing to. And the technical fancy term for that is dereference. All right, so like a pointer is, it like knows the address, has a reference to it essentially. You think of it that way. it knows how to get to it, and we can dereference it to find what it's looking at. So that will be C. So that means address of is so sad and not actually one of the answers. What's the address of operator then? Which one was that? Yeah, it's going to be the ampersand. So that's if you have an int and you would like to make a pointer to that particular int. You like to hold its address. How do we get the address of that x variable? Shove it into P. You say ampersand x. That gets the address of x. All right, so that's the missing piece. Okay, so yeah, very nice. Good thoughts. And let's go. Let's keep on trucking. So yeah, I hope that makes sense. Any questions before I talk about a brand new topic involving pointers? All right. So yeah, I want to teach you about a magical place. It's called the heap. It's where you can make memory and have it live forever, potentially, and also remove it when you're done with it, so it doesn't have to live forever. Okay, so let's remember some things. We know how to make variables that do live forever right now. We know about global variables, right? So that's if you make something outside of main or any other function, they're global, right? Things inside of functions are local memory, local variables, stuff like that goes there. But if you make it outside, you can make a big long, you can make a global variable for sure. So that's a thing, right? That's global memory you can make outside. It lives for the life of the program because you might need it in any function. Who knows, all right? And so that's one way to make variables that live forever. And like you can also make stuff that are giant, right? You can make like a giant array of size 1 million, ints. Sure, that can be global, live for the life of the program. And what happens when you make global variables like this is like C++ has no clue when you're going to need it, so it makes sure that all that memory space is made right before main even starts, because like you might need to use that stuff in main even. So all the global variables get allocated. That's what it means to make it in memory. That's a new word. Made in memory. Right as the program begins, and every global variable lasts for the life of the program until it ends. It never goes away, because like anybody could use it. Anybody might need it. All right. And that's nice and all, but like, what if you only need the size 1 million array for half of the program? You're kind of wasting space. You might run out of memory even in the second half. Does that make sense? So, like, that's also a downside to global variables. We don't like that they live forever. It would be nice to have more control, all right? Because maybe we needed that giant array only for like the first part, and then it's just wasting space for the rest of the program, and we can't use as much memory as we otherwise might want to, okay? Because we might run out. So yeah, there's something better. There's something in between. It's called the heap. Right? You can make things that live forever or until you want to get rid of them. Right? So that's where I'm going. And let me teach you a little bit more about how the program is arranged in memory, because I said like all the global data gets allocated at the start. But what does that look like? All right. So here is what your program looks like in memory when it gets loaded. All right. Every program looks like this. All right. It's made of a bunch of different sections, and I'll explain each section. Okay. So like here, the low is like it gets loaded at the lowest address, and it takes up all the way to the biggest address in your machine. Okay. In hexadecimal, of course. So the first part of your program that gets loaded into memory is the code itself, like the machine code instructions for your particular CPU architecture. Those get loaded into memory, like your program is also data in a sense. Okay, so that's called the text section. It is like the textual lines of code essentially of your program. All right, in CPU machine code form. So that's part of the memory of your program that's taking up space. And then there's a whole other section called the global data section. That's where all of your global variables live. They're going to live for the life of the program, so they get their own little special section. All right, so like this is where the main function lives. Like this is where your code lives. That's loaded into memory. This is where all your global variables live, like your one int variable, your size 1 million array. Those are all getting allocated at the start. Okay, space is made for them. And then there's a third chunk of memory that has two pieces. There's the stack and the heap, this new thing, and they're fighting for that third chunk. All right. So the function call stack, we know where that is, right? We know that that's about functions and how they like make their local variable space, and like they give up their memory once they're done being called. That takes up a bit of this chunk, and it grows towards the lower addresses if you care. So like you can have like main is the first thing on the stack with all of its local variables. Maybe it's got a few here. Main can call like the foo function, I don't know, foo, which makes some more local variables. Foo calls bar, I don't know, which has some more of its own local variables. And then once functions return, like they give up their space on the stack so that other functions can be called. So that's what's happening on the stack. We remember that. That's what it looks like in memory, really. And it's growing towards lower addresses. And this brand new place called the heap is fighting with the stack. So the idea of the heap is it's a place where you can create your own memory. All right, so it's dynamically allocated things. So you can create memory on the fly. Like I want an int right now. Bam, shiny and new. I want a giant array right now. Bam, shiny and new. And like you make those things on this new place called the heap. All right, and they can live until you're done with them. You can like get rid of some pieces of those memory, of that memory that you make on the heap, which is great. And it's fighting with the stack though. So if you allocate too many extra things, too many ints, too many giant arrays, eventually they might clash, the stack and the heap. If they ever clash, if they ever meet each other, then your program is run out of memory. Okay? You don't have any more to put stuff in. So yeah, if the ends of those things ever meet, you get a runtime error and your program runs out of memory. Okay, so that's how that works. So now you know a little bit more, but I want to teach you about this brand new heap thing. Like, what does that even mean? Dynamically allocated memory. Let me show it to you. All right. So it's when you can make and destroy memory only when you want to. All right. So like global variables, you can make stuff on this magical place called the heap that can live for the life of the program. Right? It can live forever. But unlike globals, you can tell heap memory to go and be deleted. Delete yourself, please. I'm done with you now. And so you can free it up for later uses, which is really nice. Okay. So and you can say up. You don't have to say like I want a million things right now up front. It's dynamic, which means you can choose how much memory you want to make depending on this current version of the program running. So like you can get a number from the user, let's say, like the user gives you 42, like you got that from the user, and then you can say, hey, heap, give me that many exactly things. Could have been 42, could have been a million. Go off and make me an array of size exactly n, whatever I got from the user. So you don't need to say it up front, which is really nice. Very powerful. And then once you're done with this big long array, like you do the work, like you average all the elements or something, you can say, all right, I'm done with this. So that you can then use that space in memory again for later allocations. All right, I'm going to use that word a lot now. More things on the heap can take its place once you get rid of it. That's really powerful. So it's like a global variable. It'll live as long as you want until you're done. So you have fine-grained control. Okay? So, yeah, how do you make stuff on the heap is now the question. How do you use it? It's called new. You say new and then the name of a type. It's a brand new operator. All right? So if you say new and then the name of some type like int, it will give you back a pointer. So that's why we need to learn pointers. Another reason at least. It'll give you a pointer to something of that type made on the heap for you. So things on the heap don't have names. They have addresses only. Only pointers. Okay, so you say new int, and that will create a brand new int on this place called the heap. Right, so here's the heap. If you say new int, it'll make a brand new int on the heap and give you back a pointer to it. All right, so like you use it on a line that looks like this. You're using the stack to give the name to a pointer, of course. So the stack and the heap, they kind of work together. Int star n, that's a pointer to some place. Right, int star n. And then this line is going to say new int, which makes a brand new integer on the heap, shiny and new, fresh, just for you. Ta-da. And what the new operator gives back is the address of that place. Like maybe this was address 100. This will give you back address 100, and we can shove that into n. And then you can use that memory now. It's by default uninitialized, of course. You can use it as some normal int pointer at that point. Okay? But it lives forever until you're done with it. So that sets it to 42. And then you can also get rid of it, which is exciting. Okay, so every time, you always have to say the type of the thing you want made on the heap, right? And you'll get back a pointer to that thing that got made for you. Usually it will be successful. Okay. Unless you try to ask for like 5 billion ints, that will probably run you out of memory. Okay. So, let's see here. Yeah, I think that's what I wanted to say about that. Let's start some code. Let's take a look at how this kind of works. Heap.cpp. And yeah, let's do int star n equals new int. And then you can set it, you can use it all you want. Cout star n. And then like it lives for as long as you want it to. You can get rid of it later. All right. Bam. So I mean, it's just an int variable at this point. It's not very useful. It's more useful across functions, and I'll get to that in a second. Okay. So that's how you make stuff on the heap. When you're done with something, you want to get rid of it off the heap. Here's what you do. There's a corresponding operator. We said new to make something on the heap. You say delete to get rid of it. All right. So delete gets rid of memory at some address. So you give an address through a variable usually. Delete n, we'll say, like if n is a pointer to somewhere on the heap, it'll go to that address 100 on the heap, and get rid of that memory so that it is now reclaimed, and you can reallocate stuff like another int next time and not run out of memory. All right? So that's how that works. So it's like, all right, once I'm done with n, I can say delete, and now that space has been reclaimed on the heap. All right? So nothing changes. We're just like, we're better programmers now, though. Like, we're keeping track of stuff and we're getting rid of everything that we made. So this is kind of a useless example, so let me make a more complicated one to show you the power of the heap, because like you could have just used a normal int variable here, yeah. So let's do it like this. Let's make a function. All right, let's make a function up here. Make new int on the heap to show you kind of the power. All right, so let's say up here, and I'll figure out what this should return in just a second. Up here, I'll make my new int n equals new int star n equals new int. So this makes space for one int on the heap, and save the address of that new int into n. So n is a pointer into the heap now. So it's an address of some place on the heap. I can set it to 42. I can cout star n, which cout's 42. And this does not go away, this heap thing. The n goes away because it's just a local variable, but the heap memory does not go away when this function returns. It lives forever until you're done with it. So here's what I'll do. I will return n, which means that this function now returns an int star, yeah? And I will use that heap memory down in main. Hoo-hoo. So I'll be like int star, I'll call it p this time, make new int on heap. So kind of, can you imagine what's going on here? So I'm calling this function. It's up here, it's making this thing on the heap, it's setting its values, it's printing 42, and it's giving me back that same place on the heap, and now I'm going to call it p down here. So I have it still. It's not gone, like n has been gone. I'm saving that pointer again. It's memory that lives potentially forever. Beautiful. And so now I can mess with that integer through the name p now in main, like star p equals star p plus 1. Cout star p. And then once you're done, you can delete it. Once you're done with heap memory, make sure to delete it. It's good programming. Technically, all the memory that your program ever allocated goes away once your program ends, but like eventually one day you'll make a program that never ends, like a web browser or PowerPoint or something, like it's open forever. Like you don't want to just accidentally never delete your heap memory because you'll run out of memory very quickly that way. Okay, so that's what you do. You say delete, and then the address of that place. So p is holding the address. So go to that address on the heap and get rid of it. All right. And so see if you can kind of step through this in your mind. What's going on here? So there's the first function. There's main. You see how this is going to print 42, 43. Any questions about this code? It's very interesting. So I've made some memory up here that can live forever as long as I retain its address somehow. And so I'm making sure to return it down here in main. Now I get it still. And I can mess with it through this pointer p now. But once I'm done, I should always clean up after myself. Every new should have a delete. Okay? That's the name of the game. Does that make enough sense? All right. That's the trick. Yeah, so we say delete, and we give the address of the thing we want to delete, usually through a name, and it reclaims that memory. Okay? So let's figure out how to make that size 1 million array on the heap now. Because I've told you how to make a single int. You know, you can probably extrapolate and figure out how to make, okay, let's make a new double on the heap, a new string on the heap, whatever. How do we make an integer array, though? All right, let's figure that out. We're actually going to need some new syntax, some new ideas. So let me show you a secret. Every array that you make It's actually secretly doing pointer stuff. Every time you used an array, it's really doing pointer stuff. So like this is a local variable array. If I make this a name, like that's that. I have been drawing it like this, but technically, I'll go back to blue. Technically, this is not correct for me to draw it like this. It's like there's my array. Really, what I should be doing is actually, if you say the name of that array by itself, that is secretly a pointer to the start of the array. Okay? And I'll prove that to you. So really, I should have been drawing it like this. Really, array, just the name R by itself, if that's what I'm calling this thing. It's really a pointer to the first element, which is really cool. So this is address 100. That's like the next thing in the end. If it's an int array, and the next one will be 104, then 108. R is really just address 100. It's secretly, it knows it. It has that address. Okay? Let me show that to you. Say that again? If it's an int array, every integer is 4 bytes wide. And so if you want to, you have to, like, arrays are stored contiguously. If we know that the first array starts at address 100, then the next integer must start at address 104. If it was an array of doubles, it would be 108, because doubles are 8 bytes long. Good question. Any other questions before I go to code and show you that if I just print, if I say R by itself and print it, it's going to print an address. Watch. So I'll say int R equals something. Let's have it hold stuff, 567. Just a local variable, not on the heap, just an array. And if I see out R, boop, I'm going to get an address. And not just any, oh, sorry, wrong program. Arrays, got ahead of myself. That's an address. Ooh, it's secretly doing pointer stuff, which means, let me prove to you that it's the address of the first element. There's another way to get that, right? R of 0, give me the address of R of 0. Same idea, just a longer idea. Same address. Ooh, okay. That means, okay, I know how to get the first element of the array, right? I can say R of 0, but now I have another option, don't I? I can secretly say star R, couldn't I? And that will give me the 5, because it's pointing to the first thing. 2 ways to print 5. And actually, this code, this bracket syntax, is secretly being translated for you into a dereference. It's really doing pointer stuff under the hood. All right? That's just how arrays work. So, yeah, this is R is the address of R of 0. That proves that, okay? Which means, therefore, if you dereference it, star R gives you R of 0. They're equivalent ideas. Interesting. And also, if you use the syntax and go somewhere else, it's also going to be translated into some array-like syntax, all right? Or it's going to be translated into pointer-like syntax. So actually, I want to teach you something now called pointer arithmetic. If you do R of 1, you access R of 1, it's really being translated into this. Calculate the address R plus 1 and dereference it, all right? I'll show that to you in a second. But let me draw an example of that. So if this is my array, 567, and let's say it starts at address 10, and this one's 14, this one's 18, right? So R by itself is pointing to the first thing. R plus 1, you might imagine that if you ask for R plus 1, it will go to address 11, which is like in between, like it's from here to here or something weird like that. But actually, C++ is kind of nice to us. If you say R plus 1, it will calculate address 14 because it knows that R is an int pointer. It knows that you want the next int, bless you. So that's actually really nice for us. It's not going to give me address 11, it's going to give me address 14 because it knows to go to the next int, all right? So one's an offset. It's like it knows to go 1 int later, not just 1 byte later, all right? Because it's an int pointer, okay? So yeah, that's really interesting. I hope you agree. So that means, like, that is what the syntax is doing. It's like doing R plus 0 dereference, which means this one is therefore doing, so R of 1, it's really just shorthand. What's really happening under the hood is it's calculating a new address to go to, offset from the beginning, R plus 1, 1 int later, and dereference. All right, and this is equivalent to R1. Same idea, and they're both going to print 6 because that's element 1, right? There they are. Magic. So it's just pointers at the end of the day. Isn't that interesting? Let's see what else. There's more to this. You also know about C strings, right? You can totally do this in the same way for C strings. Those are just special character arrays. And actually, because all an array is a pointer to its start, you might as well store the whole array. You can store the array in a pointer. Okay, so let me show that to you, and then we'll come full circle because you know about command line arguments already. So like I can do this. I can be like, all right, if R is just an int star, I can shove that into an int star. Int star P equals R. Okay, that's nothing new. But I can use the syntax now because we know it's just shorthand. I can say P of 2. I've just I've made an alias for R, haven't I? And this will work. This will go to 7 and give me back 7. Does that make sense? Because that's coming full circle. That's really interesting. I can set, if R is just a pointer to the star, I can set that into a normal int star, and I can use this syntax because we know what that's going to be translated into. It's like, all right, start a P, go 2 ints later, and dereference it. Doesn't even need to know that it's actually an array. Well, hopefully it is, but it just knows where it starts. It's going to go to that place in memory, and that because it's an array, it'll work like that. Does that make sense? That's really crazy, I think. New knowledge. And so, any array of ints you can shove into an int star. Any array of characters you can shove into a char star, and that is why now all of the C library functions on C strings take char stars. That is why all of your command line arguments, it's char star, right? Array of char stars. That's why. Now you know. Because, all right, it's just an array. I can store that as a pointer. Pointer to its first element. That's pretty cool. All right. I hope that makes sense. And yeah, the reason I'm telling you this now is so that we can allocate things on the heap. And we're going to get back a pointer to its beginning stuff. So now you know that char star argv, right? Now you know why it's like that. Argv bracket bracket. It's an array of char stars, and actually, because of this, there's actually another type that this could have been. You could have declared it as char star argv. How do I want to say this? And some people do it this way. I can't write an A today, sorry. Char star argv. Because it's an array of char stars. That works. Crazy. So, yeah. Now you understand a little bit more now. That's fun. But yeah, here's how you make an array on the heap now. Here's how you do it. You can make an array of ints on the heap using this kind of bracket syntax. So you can say not just new int, semicolon, but new int brackets the size you need here. And that could have been a variable. It's fine. So this is how you make an array of ints on the heap. All right. So stack heap. And once you say new int 42, it'll make you a brand new array of 42 ints. And just like everything else on the heap, it gives you back an address to where that place in memory began. So we're going to shove that into a pointer. You only get an address back, so you have to put it into a pointer, not a normal array variable or anything like that. So that's why I had to have that segue. It's like you can put that into P, it'll give you back 100, and that's how you have access to that entire array now. All right, that shiny new thing that you just made on the heap. You say new int 42, makes you a shiny new int array on the heap, and it gives you back the pointer to where it begins. Okay, so yeah, P is going to hold the starting address of that array, and you can use array syntax because it really is an array. Like this, you know what it translates into. Like this will work out, and it will let you set the values there in memory. Okay, does that make enough sense so far? Like that's how you'll make an array on the heap, and once you're done with it, you say not just delete P. Because then C++ thinks that, oh, it was just one int on the heap. Because that was the same syntax, right? Oh, it must have just been one int on the heap. No, we have to remind it. No, we made an entire array starting there. So like we have to say delete bracket bracket for an array that we made on the heap. Still give its address though. Right? And then it will go away. So let me show you that. So here is, let's make it finally an array on the heap. I'll say int star q, I guess, because I've already used p, equals new int of size 42. All right. So what's going to happen is q will hold the address where that int array starts. So we get a shiny new size 42 int array made for ourselves. Q will hold the address of the first element in this size 42 array just made on the heap. All right. So that's how that'll work. And you can use normal array-like syntax, even though you shoved it into an int star, because it is an array. Q of 5 equals 55. Like, you can go there, mess with it, get the values back, change them, whatever you want. And then once you're done with that heap memory, you can pass it around between functions because it never dies until you're done with it. You say delete bracket bracket, and then give the starting address of that heap memory. All right. So remember the bracket brackets for an array on the heap, and that'll do it. So we get our 55 printed, and you could have passed this between functions though. All right, and that's kind of the goal. Like, everybody gets to use it. Effectively, it's a global variable until, as long as you keep passing the address around, and you can delete it once you're done with it though. So you can use it for other things. All right, so that's a fancy example, I think. Are there any questions about any of that? Not too horrible? Or so horrible we can't even scream about it? Well, let's see what we're thinking. This is a hard question I'm about to give to you, but it's a great thing to check. Even if you get it wrong and come back later, try it yourself, cover up my answer once I give it to you. But I want you to make the diagrams that I've been making, because that is 100% the way that you learn this stuff. Like, I would like you to draw a diagram, please, for executing the following 3 lines. Break out paint with your neighbors. I'll give you some time to do this, but here is some code that will compile and run. I'd like you to do 2 things. I want you to draw what memory looks like after these lines have been run, first of all right? And also make sure like you've sectioned this off properly, like make boxes on the stack and the heap and tell me the difference, all right? Tell me which one's where, all right? There's a few boxes that are going to be made here. And then, once you got that down, please draw what's going to happen when you say delete P, just P, all right? And P it's a name, okay? Does the question make sense? All right? I know the answer might be hard to figure out, but I want you to try it. Struggle for a little while. I can come around and help if you're wondering about something. But see if you can get it, all right? See if you can get it. Open up Paint, maybe. Help your neighbors. Convince them that you're right. But that's my question. All right? See if you can draw the diagram. Hello. Is Paint still installed on Windows 11 machines? I don't even know. Yeah. Another 2 minutes or so to think about it. What does it mean when you say new and give a type? What does it do? What does it give you back? Feel free to make up addresses like I've been doing. Oh, this is going to go at address 100. This is going to go at address 200. That could help. Think about the types of all the boxes that you're drawing. Take another minute to think about it. considering. All right. What are our thoughts? How many boxes are going to be made? Can anybody tell me that? Think 4? Yeah. Do we agree with that? Or are we just completely lost? It's okay. This is a hard question, but I do want you to try it, and definitely come back once I show you how I might think about it. And I really do want you to cover up my answer and try it yourself. This is a great way to learn, all right? So let's think about this together. So let's run this first line. It has some weird types, but we know what everything means, all right? The second you say new int star, new some type, it's going to make a box of that type, holding that thing on the heap, all right? So you say new int star, it'll make you a box capable of holding an int star, right, on the heap. And it has an address, just like, right, if you said new int, it makes a box capable of holding an int, and it gives you that address back, okay? That's what's going to happen. And we're going to shove that address into something with a name. My hint is that everything with a name, if this is inside of a function, lives on the stack. It's a local variable. So P is a local variable. It is capable of holding the address of an int star. See that? So it's an int star star. And that will be P. That's P. It is an int star star. All right? Int star star, because the second you say new int star, that gives you a backup pointer to that int star. So it gives you back an int star star. Okay, just like whenever you got made a new int on the heap, it gives you back a pointer to that int. It gives you an int star. Okay, just like tacking on an extra star. That makes sense, hopefully. That's the type of P. And this address, let's say it's 100. Right, so P holds 100 and points to this thing that is currently undefined, but it's capable of holding in this box the address of another int, an int star. Does that part make sense? That's the first line. Please yell at me if anything stops making sense. All right. Then we do this line. So we say star P equals new int. So first thing, like the right side gets run first, we make a brand new int on the heap. All right. So that's another heap box capable of holding just a normal int, right? And we are getting back the address of that int, right? So we're getting back an int star. This produces and gives back to us an int star that we are shoving in star P. Where is star P? Which box? Well, here's P. Star P is dereference, set this box. Ooh, that's an int star. That makes sense. The type's aligned. All right? So this is going to set this box to the address of wherever this place was. So let's say this is address 200. So it'll set this to 200, and now I have this chain of pointers. That's the second line finished. Does that make sense? Are we lost yet? This one right here? So that is this part. When I say new int, that makes a brand new box capable of holding an int on the heap. Okay? And we're placing its address over here because it gives us back the address. All right, so that's that part. And now, the final line, star star P equals 42. So like, all right, I'm at P. I do one star, I get to here. That's this box, 200. If I do another star, I go to address 200 now. And now I'm looking at this box. And I'm about to set that to 42. So that, my friends, is what memory will look like once you do this code. Does that make sense? The section off between the stack and the heap as well. Everything with a name is on the stack. Everything else made with new live on the heap. So there's 3 boxes total. Any questions about that before we talk about the deletion? Yeah.
So you initialize star star P a pointer to a pointer.
Yes.
But the object that in the chain wasn't, did it even exist yet?
No.
So then, how does it know what it wants
It was just this. I made a box capable of holding an int star. That's all I needed at that point. It's just like, you can do this, right? These lines could be out of order. I could say int star p, right? Just normal stuff on the stack. And then I could make my int x, like, I want to eventually, let me do this way. I'll just make a new slide. Normally we think of it this way, like I've got an x, I want to store the address of that x. I think this is what I think that is your complaint. It's like, that makes sense, right? You have x already, let's get its address stored into a pointer. I could have done this though. This is not a problem. Like, make space to eventually hold a pointer to an int, make the int, and then set p to that address. Like, you don't have to have the int ready to start this off. Does that make sense? So, okay, that means that wasn't your question then. So that's the same idea here. Like, I didn't have this int ready yet, so I'll just keep this garbage until I have it. That's what was going on. That's this part. New int star creates this box, and it held garbage, held a question mark. Yep. But eventually, what it will eventually have is the pointer to some int. It's capable of holding an int star. Yeah, just one star on p. Star p would have brought us right here. Set to this, because it could hold an int star. I gave it the address of an int. New always gives you back an address of the thing it just made, of that particular type. Yep. Nope, new is all. You can only talk about heap stuff using addresses. You have to use pointers. So that's why we have to get good at it. You'll get good at them in 41 at least. Just wait. Just wait. But yeah, it is a little complicated at the start. Let's talk next about this line, delete p. All right? What do we think is going to happen? What is going to go away when I say just delete p? Well, we might think like, all right, this is going away and this is going away. But I'm here to tell you that that is incorrect. All right, the only thing that's going away when you say delete p is like, all right, I'm going to address 100 because that's what p holds. I'm deleting that box at that particular address. Does that make sense? So you say delete p, it deletes that box and only that box. You never said delete address 200 thing. That should have been delete star p first, right? That would have fixed that. But delete p is just like, all right, p holds address 100. I'm going to go to that box in memory that I made with new and get rid of it, right? And so I've just like you can't access this memory anymore, even though p still exists. There's actually no way to get to this int anymore. We've lost it. Like, that memory is in use. We never know how to get to it anymore. So the second you delete something, you can't go through it anymore. So that's a problem. Oh man, oh man. This is a great question in a lot of different ways. Definitely come back to it, study it, try to write this diagram yourself. But we just did something horribly wrong if we run this line. We've lost access to this thing. What's that? P is this box. That's just how heap stuff works. There's no way to delete a stack variable. It's always what it means to delete something. You say delete. It goes to that address, gets rid of that box. The original variable never goes away. You'll want to never use it, though, after that, because like it's invalid to access that memory now. That's the idea. That's just how delete works. Mm-hmm. Delete 100 or something, semicolon?
Yeah, or like realistically 0x, whatever.
Yeah, but you have no control over where your program's loaded in memory, so you can't guess an address. Yeah, these are good questions, but I think we're getting off topic, so let's keep on trucking. All right, so what just happened when you say delete p is you deleted this box, but you forgot about this box. You cannot get to it anymore. You've lost a way. You've lost the arrows. because you can't go through this place anymore. That memory doesn't exist. So what happened is we just leaked memory. That's a new word, all right? We just leaked memory, and that's just what that word means is you lose access to data that still exists. It's not going away. We just forgot its address, and it's never going to get reclaimed for the life of your program. So this is a very easy way to have all your customers hate you. Like you make like all the old web browsers back in the day, they were leaking memory all day long. And so eventually they would crash because they kept on allocating, but they forgot to delete some things. All right. So like, let me show you this example. So like int star I equals new int. So brand new int on the heap. Shiny. Let's say it lives at address 100. And so we're shoving that into an I variable, 100. All right, so that is that. That's the first line. Star I equals 42. So we're setting that box on the heap to 42. And then we're coming around and saying immediately I equals new int. So what is that going to do? Well, new int makes a new shiny box on the heap capable of holding an integer. Whee! And then whatever its address is, like it gives back that address. Maybe this is 200, let's say. Or let me draw this in green, actually. Like this line. Let me show you what it's doing in green, different color. It makes a brand new box, new int, on the heap. Still shiny. It's the one lecture I get to use this pen. And then, maybe that has some address, right? It has some address, 200, let's say. It gives back 200, and it shoves that into I. So I now changes to 200. So it's doing that, and it just chopped this pointer off. Right? It can only point to one place. And then we say star I equals 43, so we set this guy to not 42, but 43. We've just lost this place. You cannot guess an address. You don't know where it is in memory. It's just completely gone to us. We can never get to this int anymore. It's just going to take up space for the rest of our program, and we will never be able to use it again. That's a memory leak. Okay? Does that make sense to us? That's what's going to happen. All right? So we just lost access to that first integer. We should have deleted it. Okay? We should have deleted it before we messed with it. All right? This kind of stuff. So that's the goal. That's what we want to prevent in our programs. Question? That's right. Just what's a good example of that? Like this arrays program. See if I rerun it. Like remember, it's ended in C3C where the array started. Now it starts here, just completely random each time. Yeah. So you have no guarantees unless you're writing an operating system. Yeah. So yeah, we want to avoid those. And so let me finally give you like an example of using the heap for something non-trivial. Let's ask the user for a number like n. We're not sure what it's going to be up front. It could be 1,000,000, could be 42, and we're going to make an array of exactly that many things on the heap. That's going to be great. That's a good use of the heap, I think. And so then we'll ask the user for those n things and have them fill the array. And then we'll do something with that heap memory. Let's do like a sum calculation. We'll print out the sum of that array, and then once we're done using it, we'll delete it. And we'll be good C++ programmers and clean up after ourselves. All right? Let's make a new file called array sum.cpp. So yeah, let's ask the user for a number. Enter the array size. Get it. And then, all right, this is either 1,000,000, could be 42, I don't know. Let's make an array of exactly that many things on the heap. Make an array of n ints on the heap. All right. Int star r equals new int size n. So I've got exactly that many spaces in heap memory now. And so let's go in and fill it. So for int I equals 0, I is less than n, I plus plus, or for every valid index of this heap array, let's get it into that array. Enter the next element, get it, and then set it. All right, so now I've got the array filled up. I can use the normal syntax even though I'm storing it into an int star. We know that now. And now let's like sum up all the values. Let's use that heap array in some way, sum everything. And yeah, int sum equals 0 for int I equals 0, I is less than n, I plus plus again. We'll be like, oops, sum plus equals r of I. keep using it, and then like see out some. All right, see out some, and that's pretty much the program using that array. Okay, so now my question is, when can I delete the array? After, like, which line should I put the delete array call on? What do we think? Good, yes. Do you see how I am done with this array right here? Done with R. The answer is already in sum just another variable. That's very good that you noticed that. So I am done with that array right here. I can delete it. Delete. Well, it's got to be delete bracket, bracket, remember. Delete it right there. Very good. Delete bracket, bracket, R, and that'll do it. All right, so here I am making an array of some size on the fly. You can't do this in C++. Can't make a stack array. You can't do this. Because like n could have been anything, it has to know up front, kind of. This won't really work, but this totally works. You can make it on the heap instead. So enter the array size, I don't know, 5, 1, 2, and so here I am. I made it on the heap. Now I'm filling it, 3, 4, 5, and apparently the sum of all those elements was 15. But I could have made a bigger array, and we deleted it, printed the sum. I could have made a bigger array, could have made like 10, then I made a size 10 array on the heap. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sum's 55. Isn't that nice? And then, like, just imagine this was a long-running program. You could keep asking the user now for another array, right? And I could, like, keep playing this game all day long, and I will never run out of memory because I keep reclaiming that stuff. It'll just reuse that memory and reuse the first array's memory. That is the goal, and that's a decent example of the heap. All right? Any questions about that? So here I am making that array of some arbitrary size, using it, and getting rid of it. Happy enough? All right. So yeah, I think that's what I wanted to say about that. You might be like, why don't I just use a vector? Well, that's how you build vectors. So here's my nice meme of the day. When you use a vector, when you make a string, C++ string, it's actually doing heap stuff for you, because that's how you get stuff of an arbitrary size. You keep pushing back, it's going to keep on increasing the size of something on the heap. Isn't that crazy? That's exciting. So now you can make your own vector. And if you take my 41 class, I will force you to make your own version of a vector one day. So yeah, think about that. And then string, same idea. You can push back to a string too, can't you? So yeah, now you know the secrets of everything, and use them wisely. Use them to your advantage. Are there any questions before I switch gears to something weird? Alright. I'd like to talk to you now about a CSCI 41 topic. I will not test you on this. Your book, though, may give you some things about it. So you're still going to have to understand it to some extent. But I want to teach you about linked lists. It's a new concept. It's a type of data structure. So it is one of the very first things you'll learn in CSCI 41. So if you understand it now, you're going to be very well prepared if you need to take that class. I will not test you on it in this class, but you might have some Zybook stuff on it. All right? So this is a great example because maybe you're like, I don't like pointers. I don't see the point. I'm just going to make everything on the stack. I'm going to use vectors that's going to do heap stuff for me. I never need to use a pointer, right? I'll just use references if I want to pass stuff. When should I ever use a pointer? Like, I hate these things. This is your first good example of that. All right, so this is why I'm teaching it to you right now. So it's a great reason to use the heap over references or pointers. You have to do it this way. All right. So let me show you about a magical data structure. Right? You'll learn about them in 41, and I'll just show them a little bit right now. So what a linked list is, I won't even write code, I'll just draw pictures. A linked list is a new type of data structure that holds on to stuff. Like, it's a way of structuring data, that's what that means. It holds on to stuff. It's made up of things called nodes that look like this. Each node of a linked list has two pieces, and I'll usually draw it like this. Every node of a linked list has two pieces. It knows it has a single piece of data, like you can store number 1 or something. And then the second piece is a pointer. It stores a pointer to the next node in the list. So you can have a list Here's your stack. Usually you make your nodes on the heap. You do not have to understand this, but it's a great example. Your list starts off, points to the first node in the list, and then this guy points to the next node. It has a data and a next piece. A data, like we can store 3 there, and then a next piece. And when you're done with your list, to mark that it's done, you'll just use the null pointer, which is 0, or I'll draw a slash most of the time. And so this is a linked list that holds 1, then 2, then 3 in that order. Okay, so that's what it's doing. So it's just another way of arranging data, and the nodes are made on the heap. It's a competitor to arrays and vectors, because those are another way to store 1, 2, 3, right? You could have made an array that looked like this. 1, 2, 3. It's easier to do some things on linked lists than it is to do on arrays. Imagine you had space, for example, and you wanted to add 0 at the start of that array. Do you know how disgustingly hard that is? Have we considered that before? If you want to add 0 and keep everything else, you have to move these guys all like that, and then you have room to put the 0. You want to preserve everything? Is that not disgusting? That's really hard with arrays. With a linked list, it's very simple. All right, make the 0 node, set that pointer, immediate. Even if this list is 1,000,000 long. If this array was 1,000,000 long, you would have a very bad day doing that. So that is my sneak peek of linked lists. You need pointers. You need pointers to do this kind of things, and to build data structures that are convenient in this kind of way. All right. So let me show that to you in more with a different example. So yeah, adding a new thing to the beginning of something. That's really hard to do with an array. All right. So let's say we tried. So first of all, you need enough space. You have to have like an empty space slot still. Like this is 1, 2, 3. And let's say I wanted to add a 0 to the start of this array and preserve everything. This gets even worse if the array is longer, right? I need to move the 3 over here, move the 2 over here, move the 1 over here. 3, 2, 1 to open up space at the beginning, and then I can put a 0 at index 0. That is a lot of work. I have to loop through the whole array. Disgusting. Whereas, if I did this with this linked list thing, right? Pointer to the first node, we call it. Maybe this is what your list looks like. It was also 1, 2, 3. Data, next pointer, data, next pointer. And then to mark it, it's null at the end. Watch how easy it is to add a brand new node. You'll make one on the heap, set its data part to 0, set its next part to be the old first, and then you'll just chop off this point and be like, all right, the start of the list is here now. I don't have to look at anybody other than this node. I don't need to know any of their addresses. Like this could have been a 1,000,000 size list. I don't care. Is that not brilliant? That's a great way to do that. If you need that access, you need that ability, it's much faster to use a linked list. Okay? So you'll read more about this in your book, and you'll learn more than you could ever want to know in CSCI 41 if you need to take that class. All right? But how would you make each node? Like, what does this look like in memory? How would you make the struct? Struct node, by the way. I just want to show you something cool before we switch gears one last time. How would you make the struct node? So every node looks like this. It's got some data, and it's got a next pointer. So like if you want to hold int data, you got to be like, all right, it holds ints called data. Bless you, that's one piece of it. And then, what's the type of all these next pointers? It's a pointer, right? Something with a star called next. Pointer to what, though? What type? This is a little weird. It's a pointer to another node. Node star next. So in the definition of the struct, you're using the struct, which seems a little circular. It's very interesting. That's called a recursive type. So yeah, it's just really fun for me. I like this stuff. It may seem a little complicated right now, but the only reason I'm telling you about this, I'm not testing you on them, is to just convince you that using the heap as well as pointers is necessary and you need to learn. Okay? You can't do this any other way. All right. So yeah, is our brain not too much on fire? I want to show you one last thing that's going to help you as you use pointers. Are you ready? Yeah.
This concept maybe a C++ thing?
No. You can make linked lists in Java. You can make linked lists in any language that has objects and references or some concept of pointers. Java's version of pointers is like references. You can do this in Python even. Yeah. Doesn't have to be C++. Yeah, actually, a lot of the, if you want, it's all going to be about speed. Like, I want to be able to do these particular operations, and I want them to be as fast as possible. So no matter the language, you'll always be making your own data structures, or using a library that gives them to you. So yeah, it's good to know where they're coming from, though. Every language you need them in. So yeah, let's talk about one last thing. It's called GDB. And it is the greatest thing ever. If you checked out because pointers are too hard, come back to this, because this is really going to help you, all right? Because you're going to mess up so much when you use pointers, when you use the heap, like you have a whole new class of errors, right? And so this thing called GDB, which stands for the GNU debugger, will save your life, okay? So again, stands for the GNU debugger. It's made by the same people who made G++. G++ stands for the GNU C++ compiler. And it just like, it's another program that lets you run your own program inside of it, and it will give you helpful information about it. So it's just the greatest thing ever once you learn it. You'll learn it even more in CSCI 41, but this is a great time to learn it at the start. Like, it knows, even if your program crashes, it will tell you the values of the variables. It will tell you the line numbers where things went wrong. Like, it's so good. It is the best thing. The only thing you have to do to use GDB is when you compile, you attach this one new thing, this new flag, we call it. You say -G to mean, like, I'm going to use GDB. Like, be ready for me. G++ -G, it like bakes in some new ideas into your program so that it makes it easy to use GDB with it. All right, you say -G, and then you give everything as usual. Be like, all right, I want to compile foo.cpp into something called foo. All right, so just remember the -G, and let me show you how beautiful it is. Okay, so this is how you do it. Let's make a new program that just segfaults. I think that'll be the easiest one. In a complicated way, though, segfault.cpp. So here's a program with a function called and that function is going to be where a problem happens. All right, so int x equals 42, int star p equals null pointer, and cout star p. So obviously we can tell at a glance why this is going to break, but like, just pretend we didn't. Your programs will get complicated, but at the end of the day, it will still be helpful, what I'm about to show you. So, all right, you're going to compile it as usual at the start, usually. You're like, all right, let's run it. Oh, no, segmentation fault. How could this have happened? So you go back, and you're like, all right, let's compile it, -G. It still runs as usual. Like, you can still run it as normal. But now it's able to be loaded into this magical place called GDB. Okay? So let's do something I've never done. Let's do it that way this time. So I'm going to say, what you do to load a program into GDB is you say, instead of running your program with just like normal, like /segfault, just stick at the start GDB space. It's like you're loading the program inside of GDB. Okay, so hit enter, and it plops you into GDB. If your terminal is really zoomed in like mine is, it'll tell you to press enter, because it's like telling you stuff. And then eventually it'll give you a prompt. This is the GDB prompt. Okay, and so here's the program still. Now we can say, hey, GDB, run my program. All right. So you say R, you can just type run to run the program. That's a command to GDB. Say R for run, hit it, R. And look at the best thing ever. So look at what it does. Look at what it does. It says, program received, blah, 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 segmentation fault. So you'll see that. Boop. Segmentation fault. In function of this file on line 7. And oh, just for your reference, here's that line printed out for you. Is that not the greatest thing ever? Do you see that? That is going to save your life when I'm going to give you a lab to do with pointers. It's going to tell you exactly where the problem happened. And they're like, okay, that's the line. There was something wrong with this line. It looks like P was the one variable involved. You can figure that out. If there are multiple ways, of this function being called, you can figure out, like, how did this function come to be called? You can say BT, which is short for backtrace, and that'll show you the stack. This is where the error occurred. Okay, main on line 11 called It's like that. It was that call. If there were other calls, like it was that one. Main called and then got to here. It's going to print out the stack for you. Greatest thing ever again. And then, if that isn't enough, like, all right, you know, I'm really not sure what's going on still. I'm not really sure why that was causing an error. You can start printing out variables even though the program crashed. GDB is amazing. You can say print space, name of the variable you want to print, right? It'll print out that variable in your current stack frame. So we're in O right now. I can print P. Or you can be like, I have some variables in this function. Maybe X was it. Maybe the fault was X. I can say print X. Oh, that held 42. No, that wasn't the problem. All right, I have P. Let's print P. Oh, that held 0. That was the null address. I think that was why. I understand now, print star. You can even try to dereference memories. All right, yeah, you can't do that. That was a null pointer, dude. And so you can see the values of your pointers. You can see what they were pointing to if they actually were pointing to somewhere. You can print everything out, even though your program has just crashed. That's GDB. Greatest thing. Yes?
You can only do this if you include the -G.
That is correct. You can still use GDB if you forgot to do the -G, but it won't remember line numbers or anything at that point. So to give that ability, it tells the compiled program more information. It bakes in.
Is segmentation. Specifically when it tries to refer to invalid numbers.
Yeah, go back to, I think it was last lecture when I defined this. It just means like you try to access some memory that wasn't yours outside of your program segment. Yeah. Any other questions? So yeah, that's how you do it. You say GDB, just instead of running your program, just tack GDB space at the front of it. All right, and then once you're done with GDB, by the way, you say quit, Q or just quit. And it's like your program is currently being run. Are you done with it? Why? Yeah, I'm done. Get me back to my terminal, please. So this slide, come back to this slide whenever you get a seg fault, and it will save your life. Okay. So I think that's pretty much all that I wanted to say. Now you can finally laugh at this old comic, and I think that's where I want to leave us. After you've had a chuckle, let me check to see if there's more things I need to give you. So yeah, welcome to the Pointer Club. You're experts now. And yeah, I want to talk about a lab and your test, but we'll just save all that for Thursday. So yeah, the rest of the time is all yours to work on stuff that's already out.